All right, so today we'll take a look at the first part of section 7.2. So chapter 7, again, it's called Analytic Trigonometry. So we're going to look at graphing, solving equations. Some equations we solve with algebra, some we solve with the calculator. But we're going to take a closer look today at just one specific kind of trig function, and that's the inverse trig functions. So first of all, I just want to explain what an inverse is visually. You can, with certain conditions, you can take the inverse of any graph. Not just trig graphs, but any graph. And if you want to think of an inverse visually, an inverse function is a mirror image over the line y equals x. So let's graph a function. Let's graph its inverse, and we'll see if it's a mirror image. Can somebody give me a function and another function that cancels that function out? We use it a lot when we solve equations. Besides a trig function. Give me another function, and then the function that would cancel that out. About time? Can you think of one? Think of something that would undo something in an equation. So when we're solving an equation, besides addition, subtraction, multiplication, division, there's something we sometimes do to both sides to cancel out, like having to do with exponents. So that's a hint. Square root and square. Okay, so what I'm going to do is I'm going to graph a square root. I'm going to graph a square. And I want to just look at it in quadrant 1. And I'll explain more why I'm just looking at quadrant 1 in a little bit. So let's set that at 0. Let's set that at 0. So these should look like they are mirror images over the line y equals x. I need to draw the line y equals x right now. So let me put y equals x, and I'm going to put that as a thin line because I don't want it to be really a big part of the picture. I just want you to see it as a line of reflection. Okay, so let's take a look at that. Okay, so what you're looking at in blue is the square root of x. In red is x squared. And that line in black is the line y equals x. And hopefully from the picture you can kind of see that if you were to fold, like if that was a piece of paper and you folded it right on that black line, it would fold and the red graph would land on top of the blue graph. Okay, they are mirror images. And that's true for any type of function. Its inverse is a mirror image over the line y equals x. All right, so this is why I only looked at quadrant 1. Because for a function to have an inverse, it has to pass the horizontal line test, not the vertical line test. The vertical line test is used to determine if you have a function. The horizontal line test is used to determine if the inverse of your graph is a function. So think about parabolas for a second. If you draw a parabola and you draw a horizontal line, could a horizontal line hit a parabola more than once? Dylan, what do you think?
Yeah, it could.
Yes, it could. So that's a problem. If a horizontal line can hit the graph more than once, then technically your function doesn't have an inverse. Unless you only look at part of your function. And that's why with the graph in red, I focused on quadrant 1, so we're pretending the other part of the parabola doesn't exist. Okay. And the problem with hitting a graph more than once is not that we couldn't draw it, it's that when you try to do some calculations with it, you would get more than one answer. And we don't want more than one answer. Okay? When we have an inverse graph, we want to be able to do something like bring up our calculator, type second inverse sine, type something in, and we want to get exactly one answer. And we do. We don't want to get more than one answer. Well, let's look at the graph of sine. Okay, there's the graph of sine. If I put a horizontal line on that graph, could it hit it more than once? Yes. So what that means is that if we do inverse trig and we look at the whole graph, technically there's more than one answer. There's an infinite amount of answers. Okay. Let me show you what I mean. If we take sine of 30, we get a half. Let's look at the sine of 150. A half. Let's look at the sine of 390. A half. I could do this all day. I could keep making up different angles that all have the same sine. Sine of 30, sine of 50, sine of 390. They all come out to 0.5. So the problem is now with inverse trig, we're going back. So we just went in this direction. Well, what would happen when you go back? If you take the inverse sine of 0.5, second inverse sine 0.5, which answer is it going to give me? They're all correct. Well, it's only going to give me one answer. It gave me the 30. And the reason it gave me the 30 is because what the calculator does is it pretends that part of this original graph doesn't exist. It focuses on looking on one section. And we have to look at one section that would only give us one answer, okay? Not multiple answers. So let's pretend that this window is kind of blocking everything else out. And all that exists is what's in that box. So let's focus on that section. If I were to focus on that section, could a horizontal line hit what's in that box more than once? Yeah, it still could. So that's not a good section to focus on. But if we slide it just a little bit, pretty close, kind of like that, could a horizontal line ever hit that section more than once? No. So if we agree that we're just going to focus on that section, when we do inverse trig, we would only get one answer because a horizontal line would never hit that more than once. Okay? And it turns out that if we focus on that section, that's from here to here, that's negative 90 to 90. So that's why anytime you do inverse and you press the sine button on your calculator, you will always get an answer between negative 90 and 90. Always. Okay, any questions on that? Okay. So what is this? It's a horizontal distance. What do we call that on a graph? Like the leftmost endpoint and the rightmost endpoint. It's the what of the graph? Yeah.
Range.
Not the range, but that's what I'm getting at. Yeah. Yeah.
Domain.
It's the domain. So what we are going to do is we are going to restrict the domain of sine to be from negative pi over 2 to positive pi over 2. We're going to pretend that the rest of the graph doesn't exist. So we restrict the domain of the original sine function to be from negative pi over 2 to pi over 2. And that guarantees us, when we do inverse, we will only get one answer. Why? Because doing that makes the graph pass the horizontal line test. And if your original graph passes the horizontal line test, then your inverse is a function. Function means you plug a number in, you get one answer back. Not two, just one. So, when we graph the inverse, it's going to have a domain and it's going to have a range. And the way you can figure out the domain and range, it's all based on the original. Okay, the regular sine function. What did I say earlier about a graph and its inverse? It was a mirror image over what? Gracie? It was a mirror image over y equals x. So what that means, y equals x, is that y turns into x and x turns into y. That's what y equals x means. Y turns into x, x turns into y. So what do you think would happen with the domain and range if you compare them in the original and then the domain and range in the inverse? Anyone have a guess? Yeah?
Are they the opposite? Are they where they switch?
They're going to switch. Okay. So let's go back and look at the range of the original. Let's go look at that. What's the range of this original graph? What's the highest and lowest that it goes? Yep.
1 and -1.
Right. So the range in the original is -1 to 1. Well, that becomes the domain in the inverse. Okay. Now let's go back and look at the original, and let's look at the domain. Well, we just said something about the domain of the original right there. The domain of the original is -π/2 to π/2. We explained why we have to do that. So what is this domain going to become in the inverse? Yeah. And what is that going to be? It's going to be my range. So the domain in the original becomes the range in the inverse. Okay. Let's graph inverse sine and see what it looks like. So it's going to be a graph that doesn't go on forever. It has an upper and a lower bound on the y-axis. It has an upper and a lower bound on the x-axis. So it's going to be some kind of squiggle just in the middle of the screen, and it's just going to stop. So let's do inverse sine of x. I'm in degrees, so right now my domain I would be fine with, but the range is in radians. So I'm going to change to radians. If you want to do it in degrees, it would be -90 to 90. Okay. So x min, let's go -2. X max, +2. Pi/2 is about 1.57. So just to make it a little bigger, I'm going to go 1.8 and -1.8 on my range. If you set it exactly to that, it's okay. It's just going to be right on the edge of the screen. This way it'll give me a little border, so it's not right on the edge. And that's the graph of inverse sine. Okay, showing both endpoints. Let's put that over here. So that's an endpoint. That's an endpoint. Doesn't keep going. And if you were to try to graph, and I could do this, I could put the graph of sine on the screen, put y equals x, you would see that that is a mirror image for the sine function over the line y equals x. Okay, any questions on that one? Okay, let's think of the graph of cosine. If you draw cosine, does that graph pass the horizontal line test? Jay? No. Cosine and sine are the same graph. They're just phase shifts of each other. Okay, that's the only difference. So we run into the same problem with cosine. Okay, I'm just going to graph it on the screen so you can see cosine. Okay, horizontal line, we intersect it many, many times. Let's try the same thing we did last time. Let's look at negative 90 to 90 and see if that would fix our problem. So it would pass the horizontal line test. Okay, so here would be negative 90, or negative pi over 2, positive pi over 2. If I focus on what's in between the red lines, does my graph pass the horizontal line test? Abby? No. Because my graph fails the horizontal line test in that section, that means the inverse would not be a function. What does that mean? If I do inverse cosine using this, I'm going to get 2 answers. I don't want 2 answers. So, let's see if we can just take and kind of group these together. And let's see if we can just slide this a little bit and look at a different section. Let's try about there. If we focus on what's between the red lines now, does it pass the horizontal line test? Yes. So because I've now found a section that passes the horizontal line test, that means the inverse cosine function, or inverse cosine, would now be a function. Meaning, if I do it, I get a single answer. Does anybody know where the red lines are now? Yep.
Is it 0 and pi?
Yeah, it's 0 and pi, or 0 to 180. And now, let me find the page I'm looking for. So that was the domain of the original, right? 0 to pi was the left to right. Domain becomes the range. Now, how did I get this negative 1 to 1? It's the same way I got it for sine. Inverse cosine has a high value of 1, low value of negative 1. That's the range of the original. Becomes the domain in the inverse. Okay, now how about the graph of tangent? Does the graph of tangent look like the graph for sine and cosine? What do you think? Juliana, does the graph for tangent look the same as the one for sine and cosine? Is it a continuous function? Not sure. Anyone remember, what does the graph of tangent look like? Megan?
It's not continuous.
It's not continuous, right? It has these curves to it. You have to pick your pencil up at each new period. So let's graph that and see if we have a problem with the horizontal line test here. Okay, so it doesn't even have to finish, but Leo, looking at that graph, does it pass the horizontal line test?
No.
No. That means the inverse of tangent would not be a function if you look at it this way. It would not be a function. That means when you do inverse tangent, you would have to write multiple answers. Well, we can do the same thing we've been doing. Let's just focus on a section that passes the horizontal line test. Did anyone see where I could put 2 vertical lines to kind of focus on just one section that would pass the horizontal line test?
Negative 1 and 1.
Negative. Well, remember, these are going, it's in radians, so each tick mark is not 1 unit. Each tick mark is pi over 2 units.
So negative pi over 2 and pi over 2?
Yes, negative pi over 2 and pi over 2. Now, what's happening at negative pi over 2 and pi over 2 in the tangent function? You have something in this function that sine and cosine doesn't have.
Aren't they asymptotes?
You have vertical asymptotes. So with sine, it was okay to include the negative pi over 2 and pi over 2. But how about with tangent? Can I include it? No, because it's an asymptote. So the domain for the original, we're going to restrict to negative pi over 2 to pi over 2. In the inverse, what happens? The domain becomes the range. Okay, so here's my range. Negative pi over 2 to pi over 2. Notice the parentheses because I can't not include them. They're vertical asymptotes in the original. And in the inverse, remember, y's become x's and x's become y's. So in the original, you have vertical asymptotes. Where is it? In the inverse, they become horizontal. Vertical, they turn to horizontal. So the graph of inverse tangent kind of looks something like that. And it's got these horizontal asymptotes. Okay, now in the original, what's the range of tangent? Yeah?
All real numbers.
All real numbers, right? Range is up and down forever. Well, that range is going to become the domain. So the domain for inverse tangent is all real numbers. And I kind of showed you in the graph, it goes left and right forever. Okay. It's important that we know the original domain and range for the inverse functions, because what we're going to do is we're going to transform them. Okay. Maybe we'll take and shift up, down, left, or right, or stretch. So the goal is going to be to figure out, if we do a transformation, what is the new domain, what is the new range. Okay. But it all starts by knowing the originals. Any questions on domain and range for inverse sine, inverse cosine, or inverse tangent? It can be a little tricky or confusing to try to remember it, so what I usually do is I think of the original in my head. And then I remember domain becomes range, range becomes domain. Right, so we're going to look at 6 pretty straightforward properties that basically govern when I can do something like this. Sine of inverse sine of 0.6. Now what should happen when you put the sine function inside the inverse sine function? Or the other way around? Yep, they should cancel. And here they do. But sometimes they don't. Let me write it the other way around. Let's do the inverse sine of the sine of 46. Let me do it in degrees. Okay, so just ignore that last one. And it works fine. Inverse sine and regular sine canceled out, and I got the answer that was right there. But watch what happens if I do 146. Did I get back what I started with? No, I got 34. What is that 34 compared to the 146? We just talked about this in the last section. Yeah? It's a reference angle. Okay? So it's like sometimes it worked, sometimes the reference angle came back different. Well, there's a formula for figuring out when are you going to get back something different, when are you going to get back the same thing. And there's 2 formulas for each of them. One of them has the inverse on the outside, the other one is on the inside. When you have inverse sine on the outside, your argument, the thing right there, has to be between negative pi over 2 and pi over 2. So inverse sine and regular sine will cancel out for any angle between negative 90 and 90. If you go beyond that, no, it doesn't work. And I showed you an example. I tried 146. That's more than 90, and I got back a different answer than I started with. Let's look at 1b. Okay, with this one, you've got the inverse on the inside. So this one only cancels out when you're between -1 and 1. Let's see what happens if you type something in that's not. Let's try let's try 1.6. Not only do I not get the same answer back, I don't even get an answer. Okay, you can't even, it doesn't even work. And that's because, go back to inverse sine and think of the domain. Okay, you just tried to plug in 1.6 into an inverse sine function. The domain doesn't go that high. The domain only goes up to 1. So if you try to plug in 1.6, it's kind of like saying, this is 1.6 right here. It's like saying, where does that line intersect that wave? It doesn't. It doesn't happen. So any questions on the conditions for those two? Okay, let's look at the next two, and you should probably be able to figure out the conditions. Okay, the first one, it's very similar structure to 1a. Inverses on the outside, regulars on the inside. 2b, same structure as 1b. Okay. So let's think of cosine. Okay, think of the one on the inside. What did we say we are going to restrict the cosine function's domain to so that it passed the horizontal line test? Yep. 0 to pi, exactly. Now think of think of the function on the inside. What is the domain for inverse cosine? And if you're stuck on the domain for inverse cosine, think of the range for regular cosine. How high and low does it go? That'll help you figure out the same answer. -1 to 1. So these restrictions of when these formulas work have to do with the domain of the inside function. That's where these restrictions are coming from. So they're not random. They're all numbers we've just seen. Okay, and for tangent. Same structure as the other ones. Inverse, one of them has it on the outside, the other one, the inverse is on the inside. Okay. Look at the inside function for formula 3a. What is the inverse, what is the domain for tangent? What did we restrict the domain to? So it would pass the horizontal line test. To what? Okay, can anyone be a little more specific? Is when you say -pi/2 to pi/2, is it the same as this one? Is it the same as the restriction for 1a?
No, it can't be equal to.
It can't be equal to. Okay, so that's important. There's no equal to's on that because of the vertical asymptotes in tangent. And now, let's look at inverse tangent. What is the domain for inverse tangent? Think of how far left and right inverse tangent would go. I kind of drew a picture just by hand. If you can't think of that, think of how high and low tangent goes. It's the same answer. It's all real numbers, -infinity to infinity. So formula 3b always works. You almost don't even need a restriction on it. It's always true. So these 6 formulas tell us when inverse function and a regular function cancel each other out in all the cases you could possibly have. And now when we're using these to solve triangles like we did yesterday, I didn't tell you that there was a restriction. Okay? We might have ended up with a problem, like this. And then we find the hypotenuse. And I would say find theta. Well, to find theta, you could do something like tangent of theta equals 2/3. And then from this step, you would take the inverse tangent of each side. Right, something like that. So you're doing the inverse tangent of the regular tangent. The inverse of the regular. That's formula 3a. And I just said to you, oh, you just have inverse tangent next to regular tangent. You can just cross it out. What I didn't tell you is the angle had to be between negative pi over 2 and pi over 2 to make that work. But it didn't matter that I told you that. Why are you guaranteed that that answer is going to be between negative pi over 2 and pi over 2? Even though we haven't figured it out yet, it has to be between negative pi over 2 and pi over 2. How come? Yeah?
Because that's the range of intersection.
Because that's... Think about the picture, though. That's what we want to focus on here. What is theta? It's an angle, but it's not just any angle. It's an angle... Yeah?
Less than 90.
Why does it have to be less than 90?
Because the two other, like theta and the other angle that we don't know has to add up to 90.
Right. It's an angle in a triangle. Specifically, it's an angle in a right triangle. So even though I didn't tell you the restriction yesterday, I just said cross these out and you'll be fine. You are fine because theta is guaranteed between negative 90 and 90. In fact, I can guarantee you it's between 0 and 90. Right? So the answer that you get automatically fits the conditions that it needs to because it's an angle in a right triangle. That's why I didn't need to tell you this yesterday. Okay? Any questions on that? All right, so the last thing I'm going to do, kind of a little bit of review because we've done it so many other times, is transformations of inverse trig functions. They work exactly the same as every transformation we've studied all year. So, Shauna, can you tell me what A would do to our function?
Shift it left or right.
Yeah, it would shift it left or right. When would it shift left? If A was what kind of number? Yep.
Positive.
Positive. Remember, it's backwards. Everything inside the parentheses is the opposite of what you would expect. So positive would shift left, negative would shift right. Okay, so A is a horizontal shift. What about B? What kind of transformation is B? Dylan?
It's a horizontal stretch.
Yes, it's a horizontal stretch, but remember it's the opposite of what you would think. Bigger numbers compress it. So if B was 5, it would not stretch it 5 times as much, it would actually shrink it 5 times as much. So there's a couple ways you could say that. You could say stretch by 1/5, because if you stretch something by a fraction, it really gets smaller. Or you could say compress by a factor of 5. You could say it either way. How about C? What kind of transformation is C? Yep.
Vertical stretch.
That's a vertical stretch, and it does exactly what you would expect. Everything that's vertical is normal. Okay, the stuff on the outside of the parentheses is normal. Bigger number stretches bigger, fraction makes it smaller. And then the last transformation, D, that's our vertical shift. Up is positive, down is negative. What about if B or C were a negative number? What does that cause our graph to do? Yep. So the negative wouldn't cause it to shrink. Whether it shrinks or stretches would depend on the value of the number. But the negative in front of the number would cause something else to happen. Yep. A reflection. If B is negative, B is the horizontal, that's a horizontal reflection. So that's over, that's like left to right. If C is negative, that's a reflection up to down. It's a vertical reflection. Okay, so now that we just reviewed quickly what all the what all the different letters do, both of those have an effect on the domain. Okay, those affect the domain. Because they're the left and right movement. C and D affect range because they're the up and down. So when we're finding the domain and range of an inverse trig function, and I ask you about the domain, all you have to focus on is the A and the B. When I ask you about the range, you're going to focus on the C and the D. So I'm going to show you how do you find the domain first. So the way you find the domain of an inverse trig function that's been transformed is you start with the argument in the middle. Okay, you're going to make a compound inequality. So you're going to have something like something of that form. You're going to put the compound, you're going to put the argument in the middle, and then you're going to put the original domain on the left and on the right. And then solve. Okay. The goal is to get x in the middle by itself. So to find the new domain, you're going to take bx plus a, you're going to stick that right in the middle of a compound inequality, put the original domain on the left and on the right, and then solve. To find the new range, first you have to take into account any vertical stretching or shrinking, and then shifting up and down. Okay, so what does that mean? Let's just make up something simple. Let's say we had a range that went from -1 to 1. And let's say I stretched that by a factor of 2. Well, if I stretch that by a factor of 2, now my range, instead of being -1 to 1, doubles. It's been stretched, -2 to 2. And then let's say I took that range and then I shifted it up 1. So if you take -2 to 2 and shift it up 1, it would become -1 to 3. That's how you figure out the range. So take into account any vertical stretching or shrinking by multiplying each value by whatever you stretched by or shrink by, and then add or subtract a number to each value in the range. If you shift it up, you're going to add a number. If you shift down, you're going to take away a number. And that's it. That's how you find the domain and range. Okay, so let's try this one. So let's find the domain and range of inverse sine 2x. What I usually like to do is figure out, is there anything that's not changing? And if either the domain or range is not changing, just write that down right now. Is there anything here that is unaffected by that 2? Shana? The range. There is no effect on the range. So if you know the original range for inverse sine, you can write it down right now. So again, in my head, what I think of, okay, I'm thinking the range of inverse. What's the domain of the original? Oh yeah, it's where I put those vertical lines to mark it off. So what's the range of inverse sine? Yep.
Pi over 2 to pi over 3.
Yep. And you can include it. So we put brackets. Okay, domain. Create a compound inequality with the argument in the middle. 2x. I usually use less thans because I'm going to put the smaller number on the right, bigger number on the, smaller number on the left, bigger number on the right. If you switch that, you'd have to flip your signs. Okay. What's the domain of inverse sine? The original domain. Yep. It's negative 1 to 1. And now how would I get x by itself there? What would I have to do to all three parts? Divide everything by 2. So you could leave it like that. You could say negative a half is less than or equal to x, which is less than or equal to a half. Or you can write it the same way we wrote the one below. Negative a half to a half. So we have a bigger number in front of x, bigger number, compressed the graph. That's how horizontal works. Okay. Any question on example A? Let's look at B. Okay. Is there anything here that is not affected by the 1/3? But Sam?
Range.
The range. The range is not affected. That's just another horizontal stretch or compression. So we'll copy down the range. Negative pi over 2. It's a pi over 2. Now, what is that 1/3 doing? Specifically, what is it doing to my graph? Sean? Stretching it by how much? By 3. That's a stretch by a factor of 3. So if I know the domain of the original is negative 1 to 1, just stretch that by a factor of 3. So your new domain would be negative 3 to 3. If you don't see that right away, then just set up the whole problem. And then to solve that, you would have to multiply everything by 3. And you'd get exactly what we just got. Any question on example B? Okay. I'm doing a lot with inverse sine, but you could use inverse cosine, and I will switch it up eventually. But I think the next one I do something different. Okay, let's look at this one. Inverse sine of x plus 2. What can you tell me about what's going on here? Yeah, Rebecca?
It's the plus 2 is a vertical shift.
Okay, it's a vertical shift. Which way?
To the it's going
Up 2. So since she said it's a vertical shift, that means horizontal, nothing is happening because there's no other number in the problem. So that means domain stays the same. What is my range for inverse sine? Just the original range. Megan?
Negative pi over 2 and pi over 2.
Yeah, and there's really not a nice way to write this. We're taking negative pi over 2, and we're shifting it up 2, and we're taking pi over 2, and we're shifting it up 2. If I was going to graph this on a window, I would need the decimal. It's negative 3.57, positive 3.57. But as far as writing the answer, you don't have to put the decimal. Okay. Any question on example C? Okay, let's try D. 5 times the inverse cosine of x. Okay, anytime a problem only has one number in it, clearly something's changing and one thing is staying the same. One number, only one thing's happening. Okay, what stays the same here? Jan?
The domain stays.
Yep, and what's the domain of inverse cosine?
Negative 1 to 1.
Negative 1 to 1. Okay, range. Range is being multiplied by a factor of 5, stretching 5 times as much. Okay, now be careful because we're using a different function. What's our range for inverse cosine? Megan?
0 to pi.
0 to pi. So if you stretch that by 5, what would you get? 0 to 5 pi. And let's look at one with inverse tangent. Now, with inverse tangent, there's something you can't change. No matter how hard you try, no matter what numbers you put in, you can never change this. What's impossible to change with the inverse tangent? Gracie? You can't change the domain. How come? Because of the vertical asymptotes. Well, there are horizontal asymptotes, but what does that mean about the inverse tangent function? Yeah?
It's because it goes on infinitely.
Right, it goes on forever. So I don't care if you take something that goes on forever and stretch it or compress it or shift it, it still goes on forever. So anytime you see a problem with inverse tangent, you can always write that for the domain. But the range we have to think about. What's the range for inverse tangent? Leo?
Negative power 2.
Okay, and we're tripling it. So can you tell me specifically how to write it?
Negative 3 power 2 not including.
Exactly, not including?
To 3 power 2 not including.
Yes. If this was an inverse sine problem, you would have the same range with brackets. Inverse tangent, we use parentheses. Okay. Any questions on that one? Okay, this one, it's kind of like what we've been doing, just identify the transformations. What might you want to do first there? Because it's not really written in this format. Not exactly. What could I do to that equation to make it in that format? Yep.
Multiply the, like, distribute the one.
Yeah, distribute the 1/4 so then you could have this. Now it's written A, B, C, D. Now we can do it. Let's just go through it verbally rather than having me write it down. What's the +2 going to do? Jane?
It'll shift it left 2.
It's going to shift it left 2. Yep. How about the 1/4? Sean?
Stretch it by 4.
Yep, that's going to stretch it by a factor of 4 in which direction? It's going to stretch it 4 times as much horizontally. How about the 3? Caleb?
A vertical stretch by a factor of 3.
It's going to stretch it vertically by a factor of 3. And then lastly, the -5. Yep.
Vertical shift down 5.
Shift down 5. Yep. So again, we've done that a lot. So hopefully by now it seems like we know which numbers do what. Okay, and the last thing, we kind of already did this yesterday, is just how to type that in on a calculator. So I'll just practice again real quick with that. Can somebody tell me the sequence of buttons I need to press to get inverse sine? Caleb?
Second sine.
Second sine. Okay, on your calculator, if it's not a graphing one, you might have to find it in a different spot. And the answer is 30 degrees. What I usually do is I always do the answer in degrees, because if you do it in radians, this is what's going to happen. You're going to get 0.523, whatever, okay? Now, if I was going to write this answer in radians, I would not write 0.523. I would write this. Now, how did I know that pi over 6 was 0.523? You know how I knew that? I knew it because of what I did first. I did the problem in degrees. If I know the answer is 30 degrees, I can convert degrees to radians in my head, because that's a small enough angle, and get pi over 6. Where the calculator in radians is never going to tell me pi over 6. So that's why I always do the answer in degrees first, convert to radians if I have to by hand, because the calculator can't do a nice job with it. Okay. This is not one that would come out nice. So if I did inverse sine of 0.7, negative 0.7, it's just going to be a messy decimal. And if I do it in radians, it's just going to be a messy decimal. Okay, I can't do that one as easy in my head because I didn't get an integer answer. But it would be negative 0.775. Any questions on how to type in? Well, actually, what would happen with that last one? Inverse sine of 1.2. Think about the domain of inverse sine. Yeah?
It wouldn't work.
It wouldn't work. The domain is negative 1 to 1. That's undefined. So. Okay, so if you do it in degrees and you get an integer answer, try to write it as a multiple of pi in radians. I would not expect you to write b as a multiple of pi because you didn't get an integer answer in degrees. Any questions on that? Okay, so that's the first part of 7.2. We won't come back to that until after the midterm. So next week you've got shop. The next week is the midterm. The next week you have shop. So then it's, what's that, February 5th, maybe? So it's going to be a while before we get back to those sections. Okay. This homework assignment, though, is not due in February. Okay, I'm going to check this during your next academic week. Okay, so this is due the 22nd. Okay, so it's 394, 1 through 9, 13 to 20, 20 to 24, and 27 to 33.